Hello, everyone, and welcome to Talk Nerdy. Today is Monday, March 12th, and I'm your host, Cara Santa Maria. And we've got a great episode for you today. But before I dive in, I want to thank the sponsor of this week's episode, the Waterline Podcast. Guys, I've been listening. It's so fun. It's really, really informative. The most recent episode that I listened to is I went back to the beginning and listened to the pilot. It's called One and All. It's all about water pollution because, of course, as we know, there's only so much water on the planet, and we are making it absolutely toxic by all the garbage that we're dumping into it. Here's the thing. There are things that we can do to help. And this episode really features the story of the Rhine River. And there's an interview with Dr. Stoddard, who's an environmental scientist from the ICPR, the International Commission for the Protection of the Rhine. There's so much to learn. I really highly recommend that you listen to this initiative of Israel New Tech. It's called Waterline. Search for Waterline Podcast on iTunes or in your Android podcast app. All right, guys, this week I get to sit down with Alanna Mitchell. She wrote an awesome book. It's called The Spinning Magnet, the electromagnetic force that created the modern world and could destroy it. But before we dive into the interview, I want to thank those of you who made Talk Nerdy possible this week. Remember, Talk Nerdy isn't always be 100% free to download. That's because of listener support from you, the Talk Nerdy patrons. The easiest way to pledge your support is to go to patreon.com, patreon.com/talknerdy. This week, I want to thank Phil T. Bear, David J. E. Smith, Pedro M. Rosario Barbosa, Jeffrey Perez, Charles Payette, Jonathan Wright, Christian Jeffrey, The Honorable Husband, Jafe, Gabriel Felipe Hermio Gonzalez, Brian Holden, and of course, Jeffrey Sewell. Now, get this. This is the cool thing. It's almost the 200th episode of Talk Nerdy. Can you believe it? This is episode 198. So I've been trying to figure out what to do for episode 200. And I think the most fun and most practical thing, based on all of your amazing suggestions, is to do another Talk Nerdy Ask Me Anything. So I've set up a special email address. It's talknerdyama@gmail.com. Again, that's talknerdyama@gmail.com. Send me your questions. Let's turn the microphone around. And in 2 weeks, we'll have a brand new episode where I will answer all of the interesting questions, or as many as I can fit in an hour, that you send to me. So don't wait, because it's going to be pretty boring if no one asks me anything. Let's have a fun AMA, okay? Once again, that's talknerdyama@gmail.com. All right, guys, without any further ado, here she is, Alanna Mitchell. Well, Alanna, thank you so much for joining me today.
Oh, it's my pleasure, Cara.
I am really excited to talk to you about your new book, The Spinning Magnet, the electromagnetic force that created the modern world and could destroy it. And let me tell you why I'm really excited to talk to you about this.
I want to hear.
Okay, so you know this is a science podcast. You know that I've been doing science communication for several years now, and magnets are like a black box to me. I honestly don't understand them.
I totally get that. I mean, this is what drew me to the topic in the first place. It was just like, what is this weird, dark art that happens when magnets attract and repel each other? It just fascinated me.
I've said that to my physicist friends before, and they think I'm crazy for not understanding. But I'll tell you what, it's magnets and viruses. They just get me every time.
Magnets are so really so complicated. And you know what, scientists, as far as I can tell, didn't really, really understand how they work until, I'm going to say, after the Second World War. I mean, this is not something that people have known about for thousands of years. You know, they knew that there were things called lodestones that attracted each other. I mean, they knew about magnets, but they didn't actually understand the mechanism of what's going on inside the atoms of magnets until, pretty recently.
And is it really, like, at this point, it's pretty well understood, and I'm just the one who's very confused, and probably everybody who's reading your book.
It's really hard stuff. It's not trivial to understand this, I found. I mean, it took me, I have a working knowledge, but it's not like, I don't have the knowledge of a physicist. I mean, physicists really, really understand this deeply. And, people like me understand to a certain degree, but it's really tough. It's like it's not intuitive. It's almost like it almost feels like magic, in some way that this even happens. And I think one of the things that was so cool for me about writing the book was that I got to understand it. I got to peel it back a little bit and try to understand all the stuff that I never imagined I would be capable of understanding or explaining. One of the people I write my books for is my mother, who's 88, actually, and not a scientist. She's a visual artist. She's a painter. And I know always if I read something to her and she can understand it, that it's, going to fly. And this is one of those books that she can understand.
Isn't that just the joy of science journalism, really, is that you get to dive so deeply into a topic that, maybe you had only scratched the surface of before. And this, of course, is not your first book by any stretch. You've written several books, often with, well, actually, they're kind of all over the place, but with a bit of like an environmental focus, at least your first two books.
For me, they're all related. This is book number 5, The Spinning Magnet. This is the 5th book I've written. And the first one was called Dancing at the Dead Sea. And it was about biodiversity, how that system worked. The second book was about the oceans, called Seasick. And it just started with me trying to understand how the ocean worked. I had no idea that the ocean was sick, that there were a lot of problems with it. I knew people said that, but I wasn't exactly sure what that meant. And so I launched on this journey, series, I think 13 journeys in 3 years all around the world with scientists to try to figure out what was going on with the ocean. And then I wrote a book about cancer because my daughter got cancer and I needed to understand that system and how it worked in our cultural understanding of cancer, because it's not the mechanism of cancer, it's why we have the relation to it as a society that we do that interested me. And then the other book was about the finding of, I had a co-author on that one, it was about the finding of the lost ship of Sir John Franklin, who was trying to complete the Northwest Passage, and his ship was found a few years ago. This is wonderful. It's just a wonderful tale of intrigue, So to me, and then this one, The Spinning Magnet, is, going out into, away from the atmosphere of the ocean, the systems of life on the planet, of biology on the planet, and out into space, in effect. So it all, in my head, it's all about systems and how systems work.
Oh, and they're also personal. I think it's so wonderful to hear about your relationship with each of these topics and kind of what drove you into them, some more obvious than others, but obviously there's that spark of curiosity that really underlies each of these endeavors.
It's the only thing I respond to. I realized early on in my life that I have to keep following my curiosity. It's this sense that curiosity is there to be slaked. That is kind of what drives my life. I need to understand things. I need to understand how things work, why they work that way. And I need to keep learning about things. That's I guess why I do what I do.
I love it. And I detect a bit of a Canadian accent, do I not?
That could be true. Yeah. I grew up, I was actually born in the States, but I have lived in Canada for my whole life since I was 18 months old. So.
Oh, neat. I'm bemoaning the fact that I live in the States today because I just found out I lost my health insurance.
Oh my God. That's terrible. Oh.
It's part of the joy of having specific jobs and having health insurance be tied to your job. But that's neither here nor there. Let's talk about fun things today. Fun things like magnets. What I love is the sort of Victorian vibe to the cover of the book and to some of the ways that you have dived into it. Because, of course, you can't talk about the magnetic poles and the magnetic forces without talking about early discovery, can you?
It's not that we know this stuff. It's how do we know this stuff? It's really about the science of ideas, the history of ideas of science. That's what interests me. How did people come to even imagine that we could understand this stuff? What were some of those, internal conversations, that interiority? Where did that come from? And so, there's I would really call this a history of science book more than anything else, I think.
I think I'm realizing more and more, and I guess I started to realize this way back in undergrad, that I am more affected as a scientific, consumer, as somebody who's studying science and learning about science. I am much more affected by stories of how we know what we know than just sort of prose around what we know, because
it doesn't move me. It just, I don't, okay, somebody can say, yes, we know this. This is how this works. But for me, I have to know how we came to understand it. That's what gets me up in the morning,
Absolutely. And it helps me not reinvent the wheel with my own reasoning. You know what I mean? Because every day, I think every person on the planet is kind of embarking on a scientific journey. We are exposed to things, we experience things, and we want to learn about, and then we realize, oh, other people have done this before. That's exciting. So if I study what they've studied, I don't have to make all the same mistakes again.
I suppose there's that, but this was to me the absolutely most super cool thing about writing this book was just, putting these pieces together. It was like this great three-dimensional puzzle, just putting all these pieces together of how scientists figured out first one piece and then put another piece onto it. And they made terrible mistakes along the way, of course, as one does, and then figured out other pieces of it and came up. I mean, the scope of the imagination it takes to do science is what just flabbergasts me. Every time I look into anything, it's just somebody is sitting there trying to think of how do we explain this and coming up with these brilliant leaps of imagination to try to work it out. And it's just, having just dipping a toe in any of that as a journalist to try to explain it to other people is just exhilarating to me.
Oh gosh, especially with something as, like we mentioned before, quote unquote magical as magnetism, as electromagnetism. I can only imagine. Tell me a little bit about some of the earliest writings or some of the earliest discoveries around it, because this must have been attempted to be understood in a pre-scientific era, or at least when early science was talking about things like ether and ectoplasm.
Yes. Well, people, of course, had theories about it way back in the, in the Greek era. And these were all, just theoretical. But the first really, what we would consider, scientific exploration of the magnet came in 1269. So this is the 13th century. This is a crusader whose name is Petrus Peregrinus. So he was a French crusader, and he was down in Italy trying to work on some fortifications in the field in this long siege during one of the crusading episodes. And it seems like he had some time on his hands. And so he conducted in the field in this, incredibly what we would consider quite rustic. We're talking tents, we're talking, horses, we're talking, swords, and, everything you see in those medieval tapestries is right there in front of him. And yet he's thinking about, why does a magnet work the way it does? And so he does the very first experiments. And what he does is he takes probably a piece of lodestone, which is a natural magnet and a naturally occurring magnet, and he cuts it into pieces. And what he discovered, and I mean, because he thought, okay, there's a part of the magnet that attracts, and there's a part that repels another magnet. And he figured if he cut it in half, he'd isolate the part that attracted and the part that repelled. And what he found, in fact, was that it didn't matter how small you cut a magnet, it still had a part that attracted and a part that repelled. And so he invented this whole concept of something called natural instinct. He felt that there was a natural instinct in a magnet. He didn't understand why it worked, as of course we didn't until after the Second World War, really. But he was able to say that it doesn't matter how small you make a magnet, it still has these properties of both attraction and repelling. And this was incredibly new. And he wrote a brief about it to a friend, just this some copies of which still exist. And the other thing he did was put a magnet in a dish of water, and he discovered that no matter how often, so it floated on this dish of water, and no matter how often you pushed it away from north, it would still find north again. And this again was something that he did. And these are considered some of the first scientific experiments that were ever recorded in human history. And they were about the magnet. And of course, at that time, it was really dangerous to even investigate the magnet. This was considered, as you say, I mean, you've been talking about magic, and it was considered a dark magic, maybe a devilish thing. It was sort of it was a proxy for, the devil attracting you to something you weren't supposed to be doing. And I mean, there was all this, this huge mythology that has sprung up over time about what magnets are. And it exists even now. I was on the internet recently looking to buy some magnets, some big pieces of lodestone, and you go onto Amazon or any of the other sites, and there's all of this language about, you can cure all these things if you just use the magical power of magnets.
I know. People still wear those bracelets, don't they?
This vibe is still there. It's just, even though we know so much, we're in the 21st century and we have all this other actual empirical knowledge about how this stuff works. There's still all this stuff that it gets attached to what a magnet is, and that's very medieval.
Wow. So you said that was in the Middle Ages. That was
1269.
1269. Okay. Oh my gosh. And then you mentioned just kind of briefly that we didn't really fully understand how they work until after the Second World War. Okay. There's a big break in there. And of course, during that time, we've known about the compass and we've used it quite a lot in navigation, right? So did we just use it even though we didn't know how it worked?
Well, we knew, bits and pieces of how it worked, right? I mean, because if you have and really Peregrinus was the one who developed the first in Europe, developed this sort of proxy for a compass, so you could tell a little bit about, where you were in the world. But no, compasses were used. I mean, the Chinese were using compasses back in about 1100. And
oh, wow.
Yeah, and they hit Europe in about 200 years later, so 1300s, 1400s in there, and were used for navigation, primarily on the ocean. That was the main thing, and of course that coincided with the whole, the age of exploration of the world. So countries, nations, kingdoms, and wealth depended on knowing where you were in the world, especially if you were on sea and you're trying to navigate a ship. So the whole exploration of compasses became a critical part of a nation's wealth and success and empire building. And so navigators started to try to figure out more precisely how a compass worked. And what they realized at one point is that when you're using a compass and you're sailing a ship, the compass will point to something different from geographic north. And if you're a sailor, you can tell where geographic north is by where the stars are and the horizon and stuff like that, where the sun is. But if you're navigating by a compass, the compass is pointing to magnetic north, not to geographic north. And so there's this difference. There's an angle of difference between those two parts of the planet. And that is called declination. And that became this incredibly difficult scientific problem for hundreds and hundreds of years to try to figure out accurately what this angle of difference was between geographic and magnetic north, and to try to figure out how to create an algorithm, in effect, to always know what that angle was going to be. And they never cracked it. They never could figure it out. They thought at one point that if you could only just measure it once, you would always know what that angle of declination was. And in fact, what they eventually discovered was that the magnetic field that our Earth produces is so incredibly tortured, so incredibly elastic and changeable that even if you stand on the same plot of Earth on the planet several years apart using the same instruments and everything, you get a different measure of that angle of difference between geographic and magnetic north. So they realized that this was just a protean thing, not a solid, dependable thing that you could measure once and always know where it was.
Oh gosh, and how frustrating that must have been early on when there really was this conception of kind of a static universe. Like, we're talking about a time when we didn't really understand our relationship to the stars, to the other planets. Like, this is, having a reliable tool, knowing that, if we use this kind of rock and we put it inside of this little tool and we have a little hand, it will help us get where we're going. But not having any concept of why that is the case must have been such a strange experience.
And not only that, but that it wasn't always the same. So you think of, you think of things being, as you say, the universe is static, that there are rules that you can follow to find things. So, what did we do when we started navigating? We made this grid at latitude and longitude that stays the same because it's linked to geographic points, right? So we're always trying to tell where we are according to these geographic points. But if you try to add in declination into that declination, or so the difference between where the magnetic and geographic poles is, that is changing every second of every day. And not enough so that you never know where you are, but enough that you can't be sure that you're actually heading where you want to go. And so the quest to try to figure this out, to try to understand the rules that governed this force of magnetism, governed where the compass, what drew the compass. That quest became what they called the Magnetic Crusade, and it was the first international collaboration of scientists to try to map declination across the world. So try to figure out for once and for all what the formula was, to try to, no matter where you are on the Earth, what formula did you use to tell where, what that difference was between geographic and magnetic north. So scientists were and navigators and sailors were on this immense hundreds of years of inquiry to try to figure this out. And they never worked it out.
It's just fascinating. And that's even like towards the end of, like you said, this hundreds of years endeavor, because early on, we're using terms like geographic north and magnetic north, but they probably didn't even know that there was a difference early on.
Early on they didn't. And then at one point they did. They figured it out. And
then they figured it out when they got lost, right?
They figured it out when they got lost, when they crashed into an island or something like that. I mean, think of it at the beginning when sailors were sailing, when humans were in ships. At the beginning, they would just go along rivers, so they always knew where they were. And then they might have eventually went into coastal waters, and then they could follow the coast and tell where they were. And then eventually they could take soundings. If they were a little bit further out from the coast, they could, get to the bottom. They could tell where they were by, feeling where the bottom was. But once they started going across the Atlantic and into deeper waters, they couldn't tell where they were except by watching the stars. And the stars could tell them where geographic north was. But when they were using the compass, they couldn't always see the stars, right? So they had to be able to use the compass. And then they couldn't work out this formula. Why wasn't the magnetic field always the same? And they felt at the beginning that it was because, there were all these rules. I mean, if you were a sailor and you had garlic on your breath, you could be beaten or severely punished because they thought that the garlic was going to affect the compass. Like there were all these rules, but, because they didn't actually understand how, what was happening, how this thing was being measured, and that it's just so intoxicating to think about how eventually people sat down and said, okay, well then what is actually happening? What is happening to cause this magnetic field to be changeable? Because ultimately they came to that. They said, it's changing a lot. And it was terrifying. Can you imagine when they first figured out, and this was in the 1600s, they first figured out that the field is changing all the time, like from decade to decade, standing in the same plot of land and, outside of London, using the same instrumentation, that this angle of declination was different. It was like one of the truths of the universe had been altered.
Oh yeah, it's like there must be poetry about like the firmament of the earth breaking beneath their feet.
Exactly. It was like suddenly figuring out quantum field theory for the first time and realizing that what we see is not really, everything that we see. But for these guys, this is like, oh my goodness, that this field it's not always the same.
Ugh, I'm still trying to put myself in the shoes of somebody who is relying on an instrument, not understanding how the instrument even works, in an era when cartography is still like, there's so many unknowns. They're still drawing the maps of the Earth. Like it's just, it just blows my mind. But of course, then we do fast forward to a time when we start to realize that the poles are not so stable, or at least the field put off by the poles are not so stable as what we would expect. And this is when I would assume, correct me if I'm wrong, scientists really did start to understand that relationship between the Earth and this force, quote unquote, that we call magnetism.
Well, they started to realize that there were theories about this back in 1600 with, William Gilbert, did some modeling of the Earth with lodestone, and he felt that the Earth, he said at that time that the Earth is its own magnet, that the Earth itself is a magnet. And this was incredibly controversial. He said that the Earth has a magnetic soul, was the way he put it, which I love that.
Wow, that's beautiful.
I know, it's so gorgeous. But it wasn't until, well, the thing at the moment, you know how in science, you know this, but in science there are these hinge moments. There are the moments when everything changes. And one of them was in 1905. And that was that's sort of what, it was the first journey I took to try to do the research for this book, was to try to recreate that hinge moment in 1905. And it happened in France. And what I wanted to do was try to figure out what was the first scientific paper that was published that said that the Earth's magnetic poles could be on opposite sides of the planet. And that paper came out in 1906, but the research was done in 1905 by this geophysicist named Bernard Brune, who lived in the volcanic heart of France. And he, got on a horse one day and rode for hours, and took his chisels and hacked a little piece of terracotta out of a road cut that had just been made in central France. And when he took this chunk of terracotta back to his lab, he realized that at the time that this piece of rock had laid down its magnetic coordinates, which we know now was about 5 million years ago, but he didn't know that then. But he knew that rock showed that at that time, at some point, in the Earth's history, the poles had been on different sides of the planet. And he published a paper on this, and it just revolutionized science. It was so controversial that people spent decades and decades and decades fighting about it till finally they proved that, in fact, this had happened and happens all the time. And we now know that this is in the 60s, though. I mean, this is practically within my lifetime that scientists realized that the poles episodically and aperiodically shift places, and have done so hundreds of times in the planet's history. But this is again just one of those moments when it was like time is running. If we wake up and all of a sudden time is running backwards, that's that's the kind of the level of tectonic shift in the thinking that happened when scientists realized that this really happens. And that's all related to the fact that our Earth has a magnetic field that is generated within our Earth's core. So, and the discovery of all of that has has happened also just in the last 100 years or so.
Yeah, it's funny because I know it's no longer a controversial topic that the poles have flipped and the poles will flip again, that they flipped several times. In my mind, it's still a bit controversial because it hasn't happened. The time span that this takes place on is so vast.
Yeah.
Even though we're due, I suppose, pretty soon, it does still, it's basically incomprehensible to me. So I think maybe we can start to comprehend this by breaking down a little bit, what is a magnet and what is that relationship? You just started to get into it. What is going on within the Earth's core that this magnetic field is developed?
Right. Okay. Well, just to back up a tiny bit.
Yes.
One of the things that helped me a lot with this is to realize that the sun also has a magnetic field, and its field changes direction. So its poles flip every 11 years. So much more on a routine. I mean, not absolutely on a routine, but much more on a routine. So roughly every 11 years. And we can see that because the sun is plasma, basically. So we can look inside it. It's not like we can avoid seeing that. So we can see all that happen. In the Earth, of course, we've got a crust over top, so it's really a lot harder to see what's going on inside the core. But what scientists now know is that what we've got in there is and again, this is all in the last, all of this science happened after 1900. We now know through seismic readings and things like that what we've got is a solid metallic core, so iron and nickel, and a few other things. So there's a solid core. And then there's an outer core, which is the same basic material as the solid core, except that it hasn't cooled down yet. Over time, over billions of years, it will cool down. But right now, it's still molten, so it's moving. It's metallic again. It's iron and nickel, and then that is surrounded. This outer core is surrounded by the mantle, and the mantle is enclosed by the crust. So those are the four portions, concentric portions of the planet. So the inner solid core, the outer molten core, the mantle, and the crust. So what's happening is that inside the Earth is really, really hot. And this is an artifact of our planet's birth, right? The planet, as it was created, just stored a whole bunch of heat from its birth 4.6 billion years ago in the core of the planet. And I think it this way, the job of that heat is to be dispersed. So it's always trying to get out from the core. So this is convection heat. So as this heat is trying to leave the core and disperse into the mantle, disperse into the crust, disperse into the atmosphere and into the galaxy, it's moving. And as it moves, it creates convection currents. So there's movement there. So that movement within the outer core creates electric currents, and those electric currents create a magnetic field. And there's such a vast amount of heat and such a vast amount of volume in this very, very turbulent system within this outer core that it creates this giant magnetic field that runs in these unending loops and surrounds our planet and actually protects our planet from solar and galactic radiation. That's how it all works. But this field is created within the outer core, but the outer core is very tortured. It's got all of this other stuff happening in there. There's a dominant two-pole system, which is why we have a North Pole and a South Pole. But there are other sort of, you could say, magnetic factions, or I think of them as sort of rear guard actions, that are trying to destabilize this two-pole system. So there's all of this other magnetic activity going on inside that outer core. And episodically, these alternate factions overcome the two-pole system. They destabilize it. And so in order to regain stability, the main dipole's direction has to change. And so that's when the poles begin this long migration. I love this word because it's like humans, moving there. But in fact, like a trek, like they go for it. And so these two poles, instead of being where they are now, they begin to move. And as they move, the field that is generated by this two-pole dominant system diminishes, so that the dipole becomes very weak. So instead of being 100% as it is now, it goes down to about 10% of its normal strength, because all these other magnetic factions are fighting with it. So during this whole long migration, which scientists think it takes hundreds, if not thousands of years, during that whole time, instead of having two poles, we have 4 or 6 or 8 poles, as all these other magnetic factions assert dominance and also fight with this dominant dipole
what?
I know, it's like crazy. Who would think this? I mean, in my head, as I started thinking about this, and scientists don't really have, they don't have metaphoric language to talk about this. They have scientific and physical language. But in my own head, I started to think about it. It's like the battle of the Titans in there, in the core of our planet. All of this stuff is happening. There are all these, it's this immense tortured protean, changeable system in there that is almost impossible to predict. It's profoundly nonlinear. It's profoundly turbulent. And if you think about that and the fact that these poles are destined to switch places at some point, and you compare that to the way scientists used to think, or people used to think of the field as just being this static two-pole system, like a bar magnet kind of thing, when in fact there's all of this other stuff going on there. It's just, it's the great drama, right?
All right, guys, I want to take a quick break from the show to thank a special sponsor of the episode this week, Traveling in Space. Now, you may remember that a couple of years ago, I had Stephen Paul Leva on Talk Nerdy as a guest. He's a novelist. He's amazing at the science fiction genre. We talked about that a lot during the show, but we also focused on his science fiction satire, Traveling in Space. It's a unique first contact novel because it's written from the point of view of aliens as they explore our planet. Such a great book. And guys, right now, up until March 31st, so you got to get there fast, Blue Roof Press has the ebook of Traveling in Space on sale for only 99 cents. That's for your Kindle or for reading on your smartphone, tablet, iPad, or computer with the free Kindle app. And also, if you love audiobooks, the purchase of the ebook lets you buy the companion audiobook for only $7.49, which is a massive savings because it's usually $24.95. Now, one thing that Stephen talked about on the episode was how he always writes his novels with the human voice in mind. And so he was really pleased to produce and direct the audiobook himself. It features actor and podcast host Jeff Kanata doing 35 different voices as he narrates the story. That's a lot of characters. So for some funny, smart, and thought-provoking sci-fi entertainment, check out Traveling in Space by Stephen Paul Leva on Amazon right now. And I will have a link in the show notes. Click directly through and you can get that ebook for only 99 cents. But you got to act fast because it's on sale from now until March 31st. All right, guys, let's get back to the show. So what is it that keeps the poles? I mean, obviously they do migrate, and they migrate, as you said, potentially over hundreds or thousands of years. And they flipped several times throughout the history of the Earth.
Hundreds of times, yeah.
So what is it that keeps it? Wow, that is a lot. Not just several, but hundreds. What is it that keeps them somewhat where they are? Like, why does the dipole system kind of dominate all these other sort of warring factions, like you mentioned?
Part of it, it's reinforced by the spin of the Earth. The spin doesn't
Which is why they're at those points, right? That's why north and south is at opposite ends of that kind of imaginary dowel going through the planet.
Yeah, but really, the north and south I know we use planetary language, like we use the language of orbits. To describe this stuff, because that's ancient. That's the ancient metaphor that people used hundreds and thousands of years ago. But in fact, what you're talking about when you're talking about a pole is the direction that the field is flowing in. That's what you're really talking about. So the field flows from the north and goes into the south. In fact, today, what we call our north and south poles are not the north and south poles of our planet. In fact, our planet's magnet's north pole is where we consider our south pole to be.
No, that's so crazy.
I know. So when they flip, so in other words, the reason that your compass needle points to the north, is attracted to the north, is because it's attracted to the south pole.
Oh, you're right, because they're
of the planet's field, right? Yeah, because opposites attract, charges attract. So what the pole really refers to is just the direction that the field is flowing. So it goes out the north and into the south, and in these great unending loops. Like, that's the thing about magnetic field lines, is that they don't end, and that's why when you see
they're loops, like you said, this is what that picture of them coming out of these different opposite ends of the Earth and kind of looping back around. That's a better way to kind of imagine what's happening.
But that is still reflecting the dipole, because on the surface of the planet, that dipole is still. So what's happening inside the Earth, inside the core, is there are all these other magnetic fields that are also created. And if you go down to the core, to the boundary of the mantle and the outer core, which is as far as the math will take us, and this is all math that you can capture through satellite imagery and all that kind of stuff. But if you get down to the boundary of the mantle and the core, what you see is that I'm going from memory here, and don't hold me to it, but at that point, the dipole, which we feel on the surface, which we perceive on the surface as, I'm going to say 95% of the field that we're measuring on the surface, at the boundary of the mantle and the core, it's only like around 35%, something like that. So all the other magnetic factions make up the balance when you're there.
Oh, interesting. And you mentioned, too, that during these kind of great migrations, that we go from having kind of a high percentage at north and south to potentially, not just a dipole system, but 4, 6, maybe 8 poles. Where in that process are we right now? Are we like pretty strong? Are we at like 100%? Or are we hanging out closer to like 30 or 40?
No, such a good question. Such a great question. This is the thing that scientists have been trying to figure out. So we have a dominant dipole system right now. So it's not clear to scientists that the poles are in the process of reversing. In other words, that the field is in the process of reversing direction. That's not clear. There's not a consensus on that. They can't rule it out, is the way they put it, but they can't say that it's happening. They can say that it will happen for sure, because this is how the system works. The system has to, eventually the direction of the field will change. That's preordained, right? So there's the direction of the field, and there's also the strength of the field. And so the strength of the field is diminishing. And now we're talking about the dipole. So the dipole's strength is diminishing, and it's been diminishing for at least 150 years, because we started measuring it in 1840 for the first time, the whole strength. But we can calculate back through math and through rock records and stuff like that. But we've directly observed it and measured it since 1840. And so since that time, it's diminished by about 15%, something like that. in those years, but it's still historically pretty strong. So if you look back into the rock record, into the fossil record, you can tell the direction and the strength of the field at various times in the planet's history, going back millions of years. And there's this terrific study actually that was done by Catherine Constable and one of her colleagues. She's in California. She's one of the great paleo magnet experts in the world, and so they did all this calculations to try. I know, it's just glorious. It's glorious stuff. Oh, this paper, you should read this paper. It's like reading a legal brief. It is this beautiful, crisp, gorgeous paper. Anyway, and so they go back and they look at how strong the dipole was at different times before and after reversals of other eras. And historically, this is still a pretty strong magnet. So in that understanding of how this system works, that tells Kathy Constable and her co-authors that we're not right at on the cusp of a reversal. The flaw potentially in that reasoning is that it's not exactly clear how diminished the dipole has to be before a flip happens. So it's not completely clear. And is it the same with every reversal? That's unclear too. Is this a system that you can count on in that way? And they think it is. They think that you can predict that this is. How diminished does the strength of the field have to be before it needs to change direction? That's unclear. Nobody has got that, as far as I can tell. And how fast does it diminish? Just because it's diminished 15% since 1840, does that mean that pace of diminishment will continue? Does it mean that it'll strengthen up again? Does it mean that it will?
Yeah, is it linear at all?
Is it
Probably
linear?
Not.
Well, they think. There's some evidence that this is a profoundly nonlinear system.
Yeah.
So if you say, okay, well, if it continues at that rate, this is one of the things that comes up in the scientific literature quite a bit. If it continues to diminish at that rate, then we've got 1,000 years before it's at zero. And therefore, the poles won't flip for 1,000 years. But does it have to actually get to zero before they flip? Unlikely. Will it diminish at that very leisurely pace consistently? Unlikely. This is a field of study in which there are some glorious and messy unknowns, and this is one of them.
Oh my gosh, there's so much to unpack here, and there's so little time to do it. I read all the time, right? I subscribe to a ton of RSS feeds because I'm covering science on a weekly basis, and
I hear you.
Pretty much like there's like some sort of period in which a new mess of articles will come out that the poles are going to flip. So you always are coming across this are we due for another reversal? And are they just rehashing old info each time they write about this, or is there some new science that is catching our attention? And on top of that, sorry to ask you a compound question. Is this something, it's so funny because the way it's written, you always expect that it's just going to happen overnight. Yeah. But now I'm starting to understand that, no, it's probably happening right now. It's probably going to take hundreds, if not thousands of years. Maybe we shouldn't freak out about this.
It's not imminent Armageddon. That's it. I think there's nobody who's saying that among scientists. There is new information though. And the new information is coming from a couple of different places. One of them is a set of satellites that just went up into the atmosphere. It's a trio of satellites called SWARM. And they're 3 satellites that went up in 2014, and they are doing all these new measurements of the field. And they're doing the measurements of not only the direction of the field, but also the strength of the field, because those are the 2 parts of the vector that are important when you're talking about the Earth's magnet. And what they're showing more clearly than ever is not only that the strength is diminishing, of the field is diminishing, but that in your mind's eye, you go to that boundary between the outer core and the mantle. So that's where, that's as far as we can get into through math to look at this dynamo that's creating this magnetic field for our Earth. If you get there, you can see that over roughly 23% of the Earth's surface in the southern hemisphere, from on one side of Africa to the other side of South America, below the equator, you can see that the field has already reversed over that great big huge swath of the Earth's surface. And what that means is that when you take that up to the surface of the planet and then up into the atmosphere where the magnetic field, is to magnetosphere where the magnetic field is protecting our planet. What it means is that there's a sort of, I think of it as a bruise in an apple, so that our Earth's magnetic field is still there, but it's weaker over that part of the surface of the Earth. And so it's letting more galactic and solar radiation closer to the surface of the Earth over that part of the planet. And you can tell that in a bunch of ways, but one of the really important ways is that as satellites move through that part of the atmosphere, they shut down to protect their own electronic equipment. So that they can tell that there's that's one of the ways of telling. But so you've got a big chunk of the planet's field that has already reversed. Okay, that doesn't mean that they don't know enough. Physicists don't know enough to say, okay, that means that it's going to go. This is what happens. This is what it looks like when the field is going to reverse fully. That they just don't know enough to say that. But they can say that this thing is growing, that it's, that the field over top of it is weakening quite quickly, that it's moving. So it's very, very volatile, right? And so that's an indicator that something big is going on inside this outer core. So that's one thing. And it's dramatic. It's increased from, you could say, like 17% to about 23% just in the past few decades. So it's
oh yeah, that's a lot.
Covering the surface. In other words, that's a portion of the surface. And at the same time, it's also become weaker and weaker. So like that, it's a relatively swift movement just within the last few decades. And it's also moving toward the west. So that's one thing that tells you there's a lot of volatility in the core and therefore in the field.
There's so much more we could talk about with regards just to what's happening within our own planet. But of course, I'd be remiss if we didn't get to, before we ran out of time, a few other things. Like obviously there are other planets that have magnetic fields. Some of them do, some of them don't, or at least less so based on their own structure. But even beyond that, like we didn't even talk about electricity yet. Maybe you can give us a little quick and dirty about what happens when you wrap a wire around a magnet.
Oh, right. Well, so the magnetic field is part of the electromagnetic field. So electricity and magnetism are physically connected. So what happens is when you've got a charged particle, like so an electron, say, or a proton, which are charged particles, when you're looking at a charged particle and it's stationary and you're stationary, what you've got is a charged particle creating an electric field. When you're moving with respect to that charged particle and that electric field, what you've got is a magnetic field as well. So when you've got movement and an electric field, you've got a magnetic field. And that's effectively what's going on in the core of our planet to create this massive magnetic field that surrounds us all. But going back to the historic record, I mean, it was back in 1820 because these two things were considered, electricity and magnetism were considered to be completely separate. In fact, electricity was inferior. It was just this sort of parlor trick, in the 1800s. It wasn't really taken very seriously at all until a Danish scientist named Hans Christian Ørsted did an experiment, totally countercultural. Nobody expected this experiment to do anything. It was like it was sniffed at. The concept of even looking at this was really totally improbable to even look at this. But what he did was he put a battery and some wires over top of a magnet. And what he found was that, and the magnet was attached to a magnetometer that would test it. And what he found was that they were physically connected. He found that magnetism and electricity are physically connected. And he wrote up a paper in 1820 and sent it out by stagecoach, if you can believe, to all the major scientists across Europe. And of course, they all reproduced this thing. And they discovered that he was right. And so then, then this whole investigation of magnetism and electricity and how they work together began. And that was literally in 1820. So, which brings us, of course, to what happens if the magnetic field on our planet diminishes. What happens to all these electrical systems that we've created?
Because they require it, right? I mean, it's really built into the structure of basically our modern society.
Well, all of this electrical infrastructure, all the electronics that you and I are talking on, all of this stuff depends on our having a strong magnetic field to protect the infrastructure. Because if you get these influxes of, solar, radiation or solar energy or solar magnetic energy into into our planet, which happens episodically anyway. But if you get them on a more routine, then what that does is damage the electrical infrastructure that we built up without realizing that we were vulnerable.
Yeah. Oh, gosh. Oh, gosh. It's so crazy to even think about. I mean, it's like, it's one of those things that I feel like when it comes to science and science communication, there's this overwhelming comfort or kind of assumption about the way that the world works that we don't often bother to dig into, like electromagnetism, even more than maybe like quantum effects, because I think there's sort of an exotic aspect to quantum mechanics that, you know, really dazzles and fascinates. So you see a lot of science writing around it and people attempt to understand it. And it is core. It is central to the way that our electronics and our telecommunications work. But even beyond that, just basic electromagnetism is one of those things we just assume is there. It will always be there. It will never change. We don't need to understand it. It just is. But the truth is,
like gravity, right?
Yeah, like gravity. But even it could be quite, I don't know, tenuous.
What's tenuous is not the field itself. Like the electromagnetic field is simply part of how the universe came to be. It's one of the building blocks of the universe, along with the other fields, gravity and the other two fundamental physical forces. So electromagnetism is one of the four fundamental physical forces of the universe, and so it exists. But what we're talking about really is the magnetic field that is generated within our planet. So our planet's internally generated magnetic field is what is so volatile. That's what we're talking about. And so it is what protects. So the electromagnetic field of the universe is what it allows our electric infrastructure, our magnetic infrastructure, our telecommunications infrastructure to work. But it's the magnetic field of the planet that protects it from the dangers of the universe. And it's that field that is changing.
Gosh, this is cool.
Doesn't it blow your mind?
My mind is literally blown right now. Yeah. And it's so funny because that doesn't happen very often on my show. But I'm just like, I want to do a follow-up interview with you. Like I need to come up with more questions and make sense of everything, of the fields that are swirling around within the core of my own head right now.
Yeah.
The molten portion. Because there's just so much to unpack here. But unfortunately, we're running low on time. So before we jump out of this, which makes me so sad, I would love to ask you the same two questions that I ask all of the guests that I have on my show. And they're kind of big picture, kind of deep questions. So I got to ask you if you're ready for that first.
Sure.
Awesome. Okay. So I want you to think about the future and think about it in whatever kind of context is relevant to you right now, whether it's the future of your life, your work, the future of, humanity, the future of the globe, the future of the magnetic poles, whatever is irrelevant. And I want you to tell me first, what is the thing that honestly does keep you up at night? The thing that you're most kind of concerned about, the thing that preoccupies you the most, the thing that really you're worried about. But on the flip side of that, what is it that you're quite optimistic about? What is it that you're quite hopeful for?
Whew. Okay, these are small questions, right?
Just little things that you don't often think of.
Yeah, let me toss this one off. I think the thing that preoccupies me most at the moment is, strangely, it's not the magnetic field. It's because that's, I think, in our future. But what concerns me right now is the load of carbon dioxide that we're putting into the atmosphere from burning fossil fuels. So this is the high carbon world we've created. Is the way people talk about it, of course. And, so we're putting all this ancient carbon from burning fossils up into the atmosphere. And that's altering the way our planet works. So it's altering the chemistry of the atmosphere and of the oceans, making the ocean more acidic. It's pushing creatures more and more toward limits. I was just writing a piece just before I talked to you about the fact that big beetles are becoming smaller because they're living in this much warmer environment, and that's just beetles.
Wow.
That's fun. And that, and the thinking is that this will hold true for other insects as well, but we're affecting life forms on the planet in ways that we have barely begun to really understand. And certainly in the ocean, this is between ocean acidification, the warmth the extra warmth in the ocean and the lack of oxygen in dissolved oxygen in the ocean. This is a recipe for mass extinction. And so that is the thing that keeps me up at night. I think that there's plenty of evidence that we're setting the stage for another mass extinction. So the thing that gives me hope is that we're not sure whether we've hit a tipping point on that. We don't know if we've gone too far. And that gives me hope that perhaps we can pull back from the brink. And I think that it's possible. I think that it's worth trying. And I figure that if, we don't think we can, if we lose all hope there, then we're going to just hurtle toward another mass extinction, only the sixth in the planet's whole history. So I think there's still, we have all this knowledge, we have all this beautiful, beautiful, interesting science that's telling us what's going on. We are an intelligent species that can plan. We know what's going on. We actually have the technology to pull back, to make the transition to non-fossil fuel-based technologies. We can, we know how to do this. What's lacking is the cultural commitment to do it. And I think that we're smart enough to figure that out.
And the truth is, it really is only a matter of time, because at a certain point, we will feel like we have backed ourselves so deeply into the corner that we can't not. And unfortunately, it may take until we get to that place. But at a certain point, there will be overwhelming consensus that we must act.
Well, there is in almost the entire world. The U.S. is an exception on that. And there's quite a lot of understanding of it an enormous amount of understanding in the U.S. as well. But the U.S. is anomalous.
Absolutely. And the truth of the matter is that, I think sometimes living in the US, we feel that. We feel how behind we are and how much we have yet to do. And we do forget that, like you said, some of the most brilliant minds are already working on this and are making huge steps and making a lot of progress. And that makes me hopeful too, especially on the days when I open up my Twitter feed or I, turn on the news and I'm feeling a bit less than hopeful.
And a lot of those people are in the U.S. There's a huge amount of really great research being done in the U.S.
Absolutely.
State by state, city by city, university by university, community by community. There's a real movement there.
Well, gosh, Alanna, this was such a fascinating chat. I am so sad that we have to bring it to a close. You will probably be hearing from me again soon, because I just really, really enjoy talking to you about this fascinating topic. And guys, if you want to know more about it, there is a whole book that she wrote about it. It's called The Spinning Magnet, the electromagnetic force that created the modern world and could destroy it. Alanna, thank you so much for joining me today.
Thanks, Cara.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.